Thank you for the invitation and thank you for giving me the opportunity to talk here. And as a related topic to the mapping class groups, I would like to talk about the IA-automorphism group of the free group, which is a normal subgroup of the automorphism group of the free group. And this talk is divided into these three sections. In the first section, I would like to talk about some results and some recent works on the stable homology of the IA-automorphism group, IN. And here, to introduce the definition of, I will give you the definition of IN, and I will give the first homology of IN, or the aberranization of IN, and then I will introduce the notion of what is called the Albanese homology, or Albanese homology of IN. And so recently I have determined this structure of this part, the Albanese homology, so I'd like to introduce you this topic in more detail in the next section. And in the last part, I would like to talk about some relation between the Albanese homology of IN and the stable cohomology of OTFN. Morphism group of the free group with some twisted coefficients. Okay, so the last part is one of the reasons why I'm interested in this Albanese homology of IN. Okay, so let's start the first section and give the definition of IN. So let Fn denote the free group of rank n, whose generators are from x1 to xn. And let OTFN denote the automorphism group of Fn as the others set. And we have the aberranization map of Fn which is a group homomorphism, a selective group homomorphism. And this group homomorphism induces a group homomorphism between the automorphism groups. So we have a group homomorphism from OTFN to OTZN, which is isomorphic to the general linear group of rank n. And this is known to be surjective. And because we have the generators of these groups, and it is known to be surjective, and its kernel is denoted by n, and this is called the IA-automorphism group. Of Fn. So this is the definition of IN. In other words, we have a short exact sequence of groups consisting of IN, OTFN, and GL and Z. Okay. So by this definition, IN is a normal subgroup of OTFN. And we have a subgroup of OTFN called the morphism group. Sorry. And the inner automorphism group is a subgroup of IA-automorphism group in general. And if n equals 2, they coincide. Okay. So we can check this by this definition, because IAN is a subgroup of OTFN consisting of elements if it is identity under the avianization. Okay? And so in the last talk by Andrew, the Torelli group was defined, and we have this one. So one boundary, okay? So the Torelli group for surfaces was with one boundary component, Torelli group is, if you remember his talk, then the definition looks similar. And so they are related, not just similarly defined, but they have similar analogous properties. And for the surface with one boundary component, we actually have an embedding of the Torelli group to the IA-automorphism group of rank 2Z. So this embedding is induced by the embedding of the mapping class group into the automorphism group of rank 2Z. Okay. And how do you this one? So this is the IA-automorphism group, and we know the first homology, or so the IN is a group. So we want to know whether it is finitely generated or not, and it is known that the IN is finitely generated by Magnus, and Magnus gave a very nice, beautiful generations of finitely many. And we know also the first homology. And before stating first homology, I'd like to recall somewhat related to the last talk. I'd like to consider the representation structure on the homology. And in this case, I'd like to consider coefficient. And AutoFN module M. And then we can define the homology of IN with coefficients in this module M. So by restricting this action of AutoFN to IN, we obtain the definition of the homology GLNZ representation structure. So if the trivial coefficient, so the rational or integer coefficient, it is this representation structure comes from in a similar way to Andrew's talk. So we have a short exact sequence of groups. So the group on the right-hand side acts on the homology of the group on the left-hand side. So in this case, we have an AutoFN module, so AutoFN action on this coefficient. So AutoFN acts on this homology, and by restricting this action to IN, this is trivial, so we obtain the GLNZ action on this homology. Okay. And so in what follows, we will consider the homology of IN, but we will consider GLNZ representation structure of the homology. Okay. But so far, for a while, we will consider the trivial coefficient. And so the first homology was determined by Cohen. And Faber Kawasumi. In 2000. And so they determined the avianization of IN, but I would like to consider vector space over rational numbers in much forest. And then the first homology is to H, where H is the first homology of free group of rank n. So this is n-dimensional vector space. And the GL and Z representation structure of H is called the standard representation. Okay. So we know the first homology, but we do not know the second homology or higher degree homology, even the rational case. And we didn't. So the cases of Torelli groups, the second homology is known to be finite dimensional, but we do not know if the second homology of IN is finite dimensional or not. Okay. And so we like to focus on algebraic GL representations. So it also appeared in the last talk, but in the case of the symplectic group and the GL general linear group are somewhat different. So I'd like to give the definition, recall the definition of algebraic GL and Z representation again. Yeah, IN is. We don't know, but for n equals 3, it is not finitely representable. But for n at least 4, we do not know.
In fact, H2 of IA3 is.
H2 of IA3, yeah. Well, but in what forest we, so in the title says, I would like to consider stable range. Okay. So stable means n is sufficiently large with respect to the homology or cohomological degrees. Okay. And so an algebraic representation, or sometimes called rational representation, is finite dimensional vector space. And group homomorphism. Well, yeah, in word forest we only consider this case. And GRP. So this gives a GL and Z representation. And if GL and Z representation is algebraic, if each entry of this metric. So if after fixing, we can consider an element of GLB as a metric. Each entry rho A KL is a rational function on AIJs. Okay, so here in the case of GL and Z, we need to consider rational functions. So, and if this is replaced with polynomial, then it is called polynomial representation. Okay, and if the cases of a symplectic group, the dual representations are isomorphic, so we do not need rational functions. Okay.
I have a question. Is this the same as saying, so I guess the simplistic proof for GL and Z is like SL plus minus, right? Things determined even extends to that algorithm?
Yeah, I guess it's, yeah, and some kind of argument appears in the paper by Lindell, I guess. Yeah. And so is a just looking. If we look at some elements, then it is algebraicity is defined in this way. But we have some equivalence definitions by using algebraic groups. And so this is our definition. And example, there's a similar things happen as the symmetric group case. And so the standard representation is an example of an algebraic or the polynomial representation, and their tensor product also. And their dual representation is again a rational or algebraic representation. It is not a polynomial representation, but algebraic. And their tensor product is also, and their tensor products are also algebraic. And their subrepresentation or quotient representation or tensor products or some extensions are all algebraic. And moreover, we know much about them. So irreducible algebraic representations are classified by pairs of partitions. Of non-negative integers. So partition of non-negative integer corresponds to the Young diagram. And so algebraic representation corresponds to pairs of such partitions. And any algebraic representations are completely reducible. So any algebraic representation can be decomposed into the direct sum of such irreducible representations with some multiplicity. Okay. So lambda mu are pairs of partitions. N? No. No, different. Yeah. So H corresponds to 1 and 0. So partition of 1, 1, and partition of 0, 0. Okay. Like that. So okay. And the reason why we consider algebraic representations is because the first homology satisfies this condition. So the first homology of IN is isomorphic to hom H, which to H, and this is isomorphic to the tensor product of H dual on which to H. So these are sub-representations, sub-quotient representations of them. So it is algebraic. Okay. And so algebraic representations are very nice and and we hope that we wish that any degree homology are stably algebraic. But in this sense, I'd like to introduce the notion of the Albanese of IN. So IN, the Albanese homology is easily defined. So it is defined as the image of the map induced on homology by the aberranization map of IN. So this is the definition of the Albanese homology of IN, and we denote the Albanese homology by putting large A on top of homology. Okay. And by this definition, we have a selective morphism to the Albanese homology and inclusion to the homology of the aberranization of, because it is defined by the image. Okay, and these morphisms are morphisms GL representations. And the homology of aberrant group to the exterior power of them. So this is isomorphic. And we know that the first homology is algebraic, so the exterior power of them are also algebraic, and the representation of them is also algebraic. So we know that by this definition, the Albanese homology is algebraic. Okay, so the Albanese homology is a quotient of rational homology of IN, so it has partial information of it, but it is algebraic. We know that it is algebraic, so it's easy to handle than the whole rational homology of IN. And the first Albanese homology is, by this definition, isomorphic to the first homology. But in higher degrees, it is not equal. And the second Albanese homology was determined by Petit in 2005. And the third Albanese homology, I determined the third Albanese homology of IN for n at least 9, and in general degrees with n at least 3 times of homological degree. I determined this part recently, and I would like to explain in the next section. Okay. So by using this part, the Albanese part, I would like to explain our conjectural structure of the whole rational cohomology of IN. So in order to do that, I'd like to introduce the dual notion to the Albanese homology. It is called, of course, the Albanese cohomology. So the Albanese cohomology is defined in a similar way, so, and similarly denoted like this. And this is defined to be the image of the map induced on cohomology by the aberranization map of IN. Okay, and then we have the dual representation of the Albanese homology is isomorphic to the Albanese cohomology. of IN as a GLNZ representation. So, so we consider rational homology or cohomology. So the considering homology or cohomology are not so different. And so the terminology, the Albanese homology was introduced in the paper of Church-Ellenberg-Farb in 2015. But before that, so like this, or this, the notion of part, the image of the aberranization map or is just a cup-product map. So it is, the notion was really historical one. But nobody called this part so nobody used any name. So I this Albanese homology or cohomology. And so we have a conjecture structure of the whole rational cohomology of IN. And I guess this is the only conjecture appeared. And this is our joint work with Professor Habiro. And this was done in 2022. So our conjecture is for a sufficiently large n with respect to the cohomological degree, we have the isomorphism between the rational cohomology of IN and the Albanese cohomology of IN tensor with the GLNZ invariant part of the cohomology. And moreover, this GLNZ invariant part is conjectured to be a polynomial algebra with yi degree 4i. So this is our conjectural structure, and this morphism is given by the restriction of the cup-product map from right to left. So because this Albanese cohomology is a sub-representation or sub-algebra of the rational cohomology of IN, and the GLNZ invariant part is also a sub-algebra, so we have the cup-product map here. Okay, and this is not just a conjecture. We do this under an assumption. So the assumption is the stably algebraic. So is algebraic for sufficiently large and with respect to the cohomological degree, then the conjecture holds. Okay. So we don't know even the second cohomology if it is algebraic or not. But if so, then the structure, algebraic structure, is determined. Okay. And yeah, and so recently, Eric Lindell weakened our assumption of our stably algebraicity to stably finitely dimensional, as dimensionality. So. this.
What is fixed and what is moving in I and N?
For any I, so this is an algebraic structure. So for any I, if for any I, for each I, for any I fixed, N is sufficiently large.
But I mean, do you need to know this for every N bigger than some, or is it N by N? You know,
So
enough that for that same.
yeah, so let I fixed, and then so for sufficiently large N, we have this at most degree I part.
For that N, for any N,
Yeah.
which has Y, you have this.
For sufficiently large N, yeah. So this means stable. All the cohomology. Yeah. Yeah, so we can say that like this, but yeah, similarly. So yeah, okay. So if we replace star with I, then we need to change here by plus k equal to I or something. Okay. Yeah. Okay. I've observed rational coefficient case, and the question is how about the twisted coefficient? And I don't want to say much about this part, but with non-trivial coefficient. So I have just one example, trivial case. So it is the spaces of Jacobi diagrams. Of Jacobi diagrams of degree d on n component oriented arcs. So a Jacobi diagram on oriented arc. Yeah, so this is the vector space. Yeah. So, yeah. So D stands for the degree, and N stands for the number of oriented arcs, the components of the oriented arcs. And so, for example, a Jacobi diagram is on n component oriented arcs. So we have n component oriented arcs. And the diagram is drawn like this. So this is a finite graph with valency 1 or 3, and it is attached to the oriented arcs. And here the degree means the number of vertices over 2.
I have a question. I'm sorry to go back to this. You said, I'm trying to understand, I was looking up to see if I understood this. So Lindell proves this under the assumption it will be five-dimensional.
Yeah.
Does he, is this supposed to be just the, so does he then prove that that stably five-dimensional implies stably algebraic? No. Okay. So, does that right, because your statement right there is about all the homology, not just the algebraic part, right?
Not just algebraic part.
Oh, where's the word algebraic in that statement of that
Yeah.
conjecture?
Yeah. So if a sufficiently large n, it is finite dimensional. The cohomology of rational cohomology of n is finite dimensional. Then it is of this form.
Okay, so not just the algebraic part, but the whole thing.
But this is algebraic. Yeah.
Yeah. Oh, okay. So there should be the word algebraic on the left-hand side.
Algebraic. So it is algebraic. Okay. Yeah. Sorry. So the Jacobi diagrams appears in the knot theory. As a target space of the conservative invariant. So the conservative invariant is the most powerful quantum invariant for links or tangles, or bottom tangles. And so this is a classical object, just as a vector space, but we have an action of the automorphism group, of free group on this space. So we can consider ADN as an automorphism module. So we have the homology of IN with this coefficient. But in the case of the first degree homology and with coefficients in A2n, so the degree 2, only the degree 2 case, I have computed this. The GLNG presentation structure this homology explicitly, but other than example, I don't know if there is any literature. Non-trivial coefficient case. Okay. So I can see the clock when is.
If you'd like, you can have my cell phone for the timer.
Absolutely. So how? So this, thank you for 9. And so, and about, I have 20?
20 minutes.
20 minutes, okay. Thank you. And so, I have to hurry. So in the next section, I'd like to give the structure of the Albanese homology of IN. So let's construct. So let UI denote hom H, which I plus 1H for I bigger than or equal to 1. If I equal 1, this is isomorphic to the first homology. So this is just an algebraic generalization of the first homology. And we consider the direct sum of UIs and then take the graded symmetric algebra of them. And take, I don't want to give the precise definition of this part, but just we call it the traceless part of this algebra. Okay, so here the trace means the image under the dual pairing, or known as contraction map. So X tensor F to Fx. So the traceless part of this algebra means consist of an element whose images are 0 under any possible pairings of dual pairings. Okay. And so this traceless part W star is constructed in a combinatorial way. then the Albanese homology of IN is equal to this. So for n bigger than or equal to 3 times of the homological degree, we have the Albanese homology is isomorphic to Wi as GL representations. Okay, and note that this part Wi is constructed in this way, and this is representation stable. In this way, so representation stable, the notion appears in the Christian-Stoke, I guess, and it means so the homology of IN, or this Albanese homology of IN, does not stabilize in general meaning. So it is it does not stabilize as vector spaces, but stabilizes as GL representations. So algebraic GL representations. So if it is algebraic, then we know that they compose into direct sum of irreducible representations. So in that sense, the multiplicities of each irreducible representation stabilizes. Okay. No, sorry. But W1 is. I'd like to give you a graphical notion. Yeah. The definition of the trace can be. Yeah, we can define. Yeah. And so outline of the proof. So the first thing to notice is we know that this upper bound of this, so it is the ith homology, ith which exterior power of the first homology of IN, and we can compute this the irreducible decomposition of this part easily if we have computers. And so, in order to prove this theorem, what we should do is to detect Wi inside the Albanese homology, and to detect outside Wi inside this part is not contained in the Albanese homology. So in order to prove that Wi is included in the Albanese homology of IN, we use a variance cycle and contraction maps. So in order to construct homology classes, we use variance cycles, which corresponds to I suppose or mutually commutative elements in IN, and we used contraction maps to detect each irreducible components in Wi. So, and on the other the other side in order to prove that WI surjects onto the Albanese, ith Albanese homology, or equivalently the dual, no, sorry. The ith Albanese homology is included in WI, or equivalently WI dual surjects onto the ith Albanese homology. We used some graphic interpretation. H1A, H1A, IA. Yes. So H1 is isomorphic to the first homology. Yeah. Map. So if we prove this, then yeah. But so actually we have the map from here to this part, but we do not know the image is contained in the traces part. So we couldn't use. So W star is here. So if we want to construct the map to here, then we need to prove that the image is included in the list. Yeah. This one? This one is constructed by using some construct maps. So it is a very representation theory. Okay. Yeah. Okay, and so in order to prove the other direction, we used two things. So the first thing is by definition of the Albanese, we have a surjective map from here to here, and so this gives the upper bound of the Albanese homology, but take quotient by the ideal. Where L2 is the kernel of the map between the second cohomology, induced by the urbanization map, like this. Okay, so this is by definition of the Albanese cohomology, we have this surjective map, well defined. Even if we take the quotient, it is well defined. So we know the upper bound here, and what we did is to prove that WI dual is isomorphic to this quotient for n at least 3i. So we have this isomorphism, and in this part we use some graphical interpretation. And half of this part, I owe this part to Lindell, Eric Lindell. And so in his draft or paper, he used in terms of word algebra or downward Brouwer algebra, but in our paper we use the terminology of wheeled plop. So our notations are wheeled prop or non-unital version. But having Lindel's or downward Brouwer algebra, no categories. And they look similar to me, and so we use these kinds of interpretations, and we obtain this isomorphism. Okay, so this is the outline of the proof of this theorem. And I have enough time. So related to this part, I would like to go into the last section about the relation between the Albanese homology or cohomology and stable cohomology of Oda-Fan. So we consider cohomology of Oda-Fan with coefficients in HPQN, which is H tensor P, tensor H dual tensor Q with N. So H is n-dimensional vector space. Okay. And I guess this will appear in the talk of Christine, I guess. No, I guess this topic appear in your talk. Yeah, but I just want to say the stable cohomology. So in Christine's talk, I guess homology version appeared, but we want to consider the cohomological version. So we have the opposite direction. PQ. And so we have the inverse limit of this. Sorry. And so in the paper of Kawazumi Vespa, in I guess 2023 published, or more earlier result, I guess, but they constructed a wheeled plop H, whose home space is this stable cohomology. Stabilizes, and so the space is defined as the stable cohomology. So I explain what is a wheeled prop, or even the prop. But so a wheeled prop, or just the prop is a symmetric monoidal category with objects are non-negative integers, and so the home space can be morphism can be written like this. So from PQ to Q, then it has some P input and Q output. And the monoidal structure gives a vertical composition. The category structure, so the composition of morphisms, gives something like a vertical composition. And it also has a wheeled structure, so it gives something like this kind of operation. It means it corresponds to some contraction map. And they are given, in that case, given by the cup product of the cohomology of autofan and the composition for the coefficients A2. The wheeled plot structure for that stable homology is defined. And in a similar way, we can define a wheeled plot corresponding to the GLNZ invariant part of the Albanese cohomology of IN. So, sorry. With APQ is, so we have, in a similar way, we have like this, and this stabilizes because of this main theorem. Okay, and so what is the relation between these two wheeled plots? So it is given by the inclusion map. I from IN to autofan induces an isomorphism of these wheeled blobs. So like this. So in terms of wheeled props, we have an isomorphism, and this means that the stable cohomology of fan with coefficient in HPQ is isomorphic to this GLNZ invariant part. And we have not, I guess, strict, but have some stable range of this isomorphism, but it is not what I want to get, because the stable range for the Albanese homology of I is 3 times of degree I, and this isomorphism is not now, it is not just equal to 3i, but somewhat bigger than 3i. Okay, so I'd like to stop here. Thank you for your attention.